Yes, the output resistance of the op-amp is not very low in this case. So can we use a voltage follower after this? Certainly you can. Firstly, if you have a resistive load, the output resistance doesn't matter. What is the significance of output resistance here? If you can expect your load resistance to be heavier than the output resistance of the op-amp, I think, right? Because what is the gain of the second stage? What? This is the DC gain of the second stage. And what's a typical value for this? What do you think is the value? I mean, is it 1, 10, 100, 1000? What? Maybe somewhere between 1 and 10. That's probably not 1. Why is it not 1? Why would you not design the output stage with a gain of 1? So, the good thing about this particular stage, which has a common source amplifier and a current source, that is one transistor on each side to the supply, is that it can support a large swing. If you have a gain of 1, that means that the swing at this point is the same, which the previous stage cannot support. Okay, you will not be able to use the full swing. So, ideally you should design it so that this will give you the full swing, VDD minus 2 VD sat, and the gain is enough so that the previous stage is operating properly with the output swing divided by the gain. Okay. So, the gain may be like 5 or 10 or something of the sort. Now, even for minimum length devices, the intrinsic gain of the amplifier will be of the order of 10 or 20. Okay. So, you can expect GDS11 and GDS12 to be still smaller than GL. Okay. Now, the problem with using a voltage follower is, let's say, instead of this load, I have a voltage follower. What is the swing of this? It definitely reduces because this can go up to VDD minus VD sat 11. So, this can go up to that minus VGS. So, you are losing a lot of swing. This is one reason why source followers are not very popular in present day CMOS technologies, okay, where the available voltage is small. Before, if you look at traditional op-amps, or if you open up the block diagram of 741 op-amp, you will have emitter followers at the output. You will have class AB stage, which consists of a PMOS and an NMOS, PNP and an NPN emitter followers. You do lose like 1.5 volts in that process, but your supply voltages may be 30 volts, so it doesn't matter. Whereas now you can't do that. So even when you make class B, the original CMOS class B stages were also using source followers, but you can't use it now because it just consumes too much headroom and will not supply enough swing. Okay. So if you are limited by swing, probably the source follower is not a good choice. Okay. So, if let's say you have a purely capacitive load, okay, that's the extreme case, right? Purely capacitive load, you can get high gain in both two ways. One is to make, let's say, a telescopic folded cascode op-amp. Let's not go to telescopic because there we know the swing is going to be relatively small, right? In a folded cascode, you do get high swing, not as high as this, but high enough. And you can drive a capacitive load with a large gain, okay. But this may still be preferable. The two-stage op-amp gives you a higher swing, right? In that case, you get a higher swing as well as you get a high frequency second pole. Okay. So, what was your question? Whether you can drive? No, second stage's gain is limited by this, right? You don't have this one. You will have the intrinsic gain of the second stage, GM11 by GDS11 plus GDS12, which can still be easily of the order of 10 or 5. Okay. It's not a problem to get a gain of 5 in that stage. So, the function of the second stage in a two-stage op-amp is not to give you DC gain. Okay. What would you do? I have this op-amp and I have a gain of 500. I want to make it maybe 5,000 or maybe even higher, like 10,000. What will I do? What is? So, how will I do that? I would, if I want to increase only the DC gain, right? I have not changed the load conditions, I have not changed the capacitance. So, my second pole and all those things have not changed, right? So, I don't have to change the second stage. I need to get just enough gain in the second stage so that the first stage operates without having to drive a large swing. That's all. Okay, gain of 10 is quite adequate, usually. Okay, so what will I do? Now, I want to increase the gain from 500 to maybe 10,000. First thing is, I try to increase the DC gain by increasing the DC gain of this stage. Okay. Now, I don't have to use a simple differential pair here. I could use a telescopic cascode. Okay. So, that will straight away increase the gain of the first stage without doing anything to the second stage. So, just like when you go from a differential pair to telescopic cascode, your frequency response remains more or less the same. There are of course some additional poles. If you replace this input circuit with a telescopic cascode, again, you are more or less set. Your stability criteria is almost always satisfied. Of course, you still have to take into account the parasitic poles in the telescopic cascode, but usually that's not a big deal. So, if I want to increase the gain, I would not try to increase the gain of the second stage. Okay. I would try to increase the gain of the first stage. Now, what length would I use in the output stage? I mean, would I use minimum length? Would I use much more than minimum length? What should I use? Yeah, okay. Maybe, in fact, the other way around, I will decide what length to use and then use an appropriate current mirror. There is no need to say that I will bias it from here, right? I mean, the output stage is more important than this particular diode connected transistor. So, if I want to use a different length in M12 and this transistor, I will simply make another mirroring branch. Okay, I will not try to somehow force M12 to match this. I will make the biasing branch to match whatever I want here. Okay. So, should I use minimum stage, minimum length? What should I use? What's your feeling? Huh? See, again, the second stage, what is the function of the second stage? If there is a resistive load, the DC gain is approximately GM11 by GL. Okay. But if you have only a capacitive load, then what is the effect of GM11? It will clearly not have any effect on, rather, the DC gain will not be GM11 by GL, it will be GM11 by GDS. What is more important, the GM of the output stage or the GDS? GM also affects the second pole, right? This is in both cases, by the way. This is in the extreme approximation where CC is much greater than CP. Okay. So, the bottom line is the final stage GM is what is important, not so much the GM by GDS ratio. So, you use close to minimum length. Of course, you go away from minimum length in cases where somehow with minimum length you can't even get a gain of 5. Okay. Then you maybe make it slightly more than that. But generally, there is no reason to make it anything other than minimum length. Okay. Because if you use something more than minimum length, you have to use a proportionately larger width to get the same GM with the same current. What is the effect of that? Huh? So, I will make this larger, keeping the aspect ratio the same. So, this capacitance will increase. Okay. And of course, the output parasitic also will increase. So, that's not good, for frequency response. The output pole will start moving in. Okay. The bandwidth will reduce. So I would generally not think of the second stage optimization for DC gain. Okay. I want to get a good GM from the second stage so that it can either drive a heavy resistive load or heavy capacitive load. In case of heavy resistive load, you need to get enough DC gain. In case of heavy capacitive load, you should, the GM should be sufficient to place the second pole beyond the unity gain frequency. Okay. So generally the GM of the last stage is important. What are the disadvantages of using minimum length in general? Low output resistance. We have already said that doesn't matter. Other thing is if you use short length and short width, the area is small. So the mismatch is worse. And the flicker noise is worse. Again, those things don't matter because it's in the second stage. It's preceded by some gain. Okay. So the length of the second stage can be reduced safely without affecting most of your op-amp parameters. Because the output impedance of second stage usually doesn't matter. Then the flicker noise and offset are not very important because they are preceded by high gain. Okay. So there is no reason to go to long lengths. The usual reasons to go to long transistors are flicker noise, offset, things like that, output resistance. But there is no reason to do that in the output stage of a two-stage op-amp. Okay. Okay. The question is, how do you ensure exact current mirroring in M12? How will you do that? How will we ensure exact current mirroring? What is the problem with the current mirroring the way it is now? VGS is the same, but VDS is different. So if we want to make VDS also the same, what do we have to do? Cascode where? So here. But that will reduce the output swing. Okay. So again, when you want to fix some biasing stuff, right, you should fix the bias branch, not the main functional part of it. Okay. It's not that you fix the functional part to suit your bias properly. You fix your bias properly so that it suits the functional part. So right now, what is the output voltage? Again, this, of course, the mirroring will be accurate only in quiescent conditions. The output swing is quite large. So that means that as the output swings, the current can be inaccurate. So let's fix it only in quiescent conditions. What is the quiescent output voltage? 0.9. Actually, it depends on how you put it in feedback, right? If you use an op-amp in feedback, what is the quiescent output voltage here? Huh? So it is basically the quiescent voltage at this point. Of course, it's logical to choose 0.9 volts in a 1.8 volt supply to be the quiescent point, but it doesn't have to be. Okay? Because the quiescent output of an op-amp is fixed only in closed loop, and it depends on how you have the feedback network, right? In this case, if this is some V bias, the output quiescent voltage will be V bias. Okay? So maybe it is 0.9, maybe it is something else. So let's say it is 0.9. Now what do we have to do? So obviously I can't mirror it from here, right? There is no guarantee that this is 0.9 volts. So where will I derive this bias from? How will I do it? We have discussed this while discussing the biasing circuits. Obviously it has to come from some other transistor which carries the same current density. Okay. That was the idea with the current mirror also. Right? Now, the problem with this is, of course, now VGS is replicated, VDS is not. So I have to arrange this part of the circuit slightly differently. What do I do? What are all the different ways of biasing a transistor at a given current? Okay, in this case, in fact, you don't even have to think of a different method. What we were doing was, we were sensing the current at the drain and feeding it back to the gate. Okay, but we were using a direct feedback connection. We were shorting this drain to gate, which meant that the drain voltage was supposed to be equal to the gate voltage. What do we want the drain voltage to be? 0.9. Okay, so how will I arrange it? I still need the same sense of feedback, but so you will use this. We have seen the circuit, right? So which is plus and which is minus? Lower one is plus. And what is this? 0.9. So if we have a circuit like this, then the drain is biased at 0.9 and gate is biased at whatever current and whatever voltage is required to have this particular current density. Okay? So the mirroring is exact. Is this okay? In general, let's say you have a current source and its quiescent output is V bias out. Okay. It is somehow being operated with this particular voltage in the quiescent condition. Now we want to mirror the current. So you sense the difference between the desired current I0 and the current through this transistor, let's say IRF, and the current through this transistor, and you feed back. Now how you feed back determines what the drain voltage is. Okay. So I can certainly do this, where this voltage is 0.9 volts. Okay. How do I make this op-amp? I'll make another two-stage op-amp, but this is a voltage follower. So one suggestion is to use a voltage follower. Will that work? I mean, this is also a circuit that is used. Okay. So first of all, what is the voltage at this point? It is 2 VGS. So it may or may not be close to 0.9. If it is close to 0.9, well and good. Then what else is the problem with this as the circuit? Is it complete? There is no bias current for the voltage follower. How do we do that? Connect a resistor. Or can I do it with a current source? Well, the problem with, okay, I can use a resistor. What is the problem with using a resistor? The impedance is okay. The main problem is that this voltage is the VGS of M1, ref for a current of IREF, which can vary with process and temperature, and the resistor has its own process and temperature variation, so the current can vary a lot. I would like a better current source than this. How will I do that? What will I, first of all, to make a current source, what do I need there? How do I make a current source? I will have to use a MOS transistor, right? Where will I get the bias from? So this is already a reference, right? That corresponds to IREF flowing through MREF. So I can connect it. I can connect it here. Okay. I already have the reference voltage available, right? If I ask you to make some current source arbitrarily, what would you do? You would just do this, right? You would make sure that this, the length of this is the same as the length of this to get reasonable mirroring. So I do the same. I use this current itself to bias our voltage follower. Okay? Is this okay or no? No, that is not ensured in this. If you use a voltage follower, that won't happen because the voltage at this point is only dependent on VGS of this and VGS of this. Okay? So if it happens to be close to 0.9 and varies a little bit around it, it may still be better than just diode connecting this transistor. Okay? But it doesn't actually make it very good. So what do we need to make it robust in that respect? So again, just to remind you, the circuit we had was this. So what will I use here? Pardon, come again? I didn't hear. So I will do this. Is that what you are saying? Output. No. See, we want to make one op-amp which we can use independently of this op-amp, right? Actually, I didn't completely get your suggestion also. So I have some op-amp and this is the bias arrangement inside that op-amp. But of course, I don't want to use that op-amp to bias this. Or, that op-amp is for whatever function it is designed for. What is okay, we tried a straight connection, that seems not to do the job. Then we tried a voltage follower, that also doesn't do the job. What's the next step? What's the next complicated circuit, Huh? We know how to make op-amps now, right? We use the simplest op-amp that we know. Okay. What is that? What is the simplest op-amp we know of so far? The single stage differential pair. Will I use an NMOS or a PMOS differential pair here? Why? NMOS or PMOS? Why? Okay. What about the output? Output goes to the NMOS gate, right? So you should use an NMOS active load, something like that. Okay. This is at 0.9 and I want a positive gain. There are a couple of ways of doing this. If I use a full-fledged differential pair, this is what I'll get. Okay. So, this is the positive input, this is the negative input of this differential pair and this is the output. This is exactly the connection I had before, okay. All I have done is to do this. So now, is the quiescent output condition satisfied? This is not just for an op-amp. Anywhere you want a very accurate mirroring, you will use this. Okay. You look at the voltage to which the current source is driving its current, and you make sure that on the reference side it is driving the same, reference side the VDS is the same. Okay. So is the circuit complete now? Or do we need to add something? Will it work as we expect it to work? Forget that this is a bias circuit. Let's think of this entire thing from this inputs to this particular output. What is the circuit we have? From these two inputs to this particular output. It's a two-stage op-amp. So what do we need? Compensation. So the circuit will not be stable. Okay. Because what is the pole at this point? What's the pole value related to roughly? It's the GDS of this transistor plus GDS of this transistor divided by parasitic capacitance here. And what about here? It's the GDS of this transistor and the output resistance of the current source, output conductance of the current source divided by parasitic capacitance here. They'll be of the same order. It is in fact a two-stage op-amp. So what do we need to do now? No, but if it is oscillating, that's it. The circuit doesn't care whether you think you want it in DC or AC, right? It will start oscillating. What will you do? You look at it, look at this output, any point in the circuit in an oscillator, it will have some oscillatory waveforms. Okay? So what do I need to do now? Compensate it. If it's oscillating, I have to compensate it. How do I compensate it? Yeah, like what do I do now? Where do I connect what? Drain to gate of MREF. If you think about it, this part is the first stage of the op-amp, this entire thing, and this is the second stage. We already know how to compensate a two-stage op-amp. And that we do by connecting a resistor and capacitor in series, or you can connect only a capacitor. Actually, let me connect only a capacitor. For now, it will compensate it. Okay. So what is the high frequency equivalent circuit? At very high frequencies, what happens? So, at very high frequencies, this capacitor acts like a short circuit. So, the circuit you have is, you don't have the op-amp basically. Okay. It's as though this part is not there. So, you have the diode connection for high frequencies and an additional gain for low frequencies. This is in general true of all compensation techniques. What compensation does is to bypass something for high frequencies. Okay. So when you have multiple stages in a feedback loop, it will tend to oscillate because of delay through each stage. Especially if the delays are comparable, it will definitely tend to oscillate. So you bypass one of the stages using this capacitor. That's another way to think about compensation. Is this clear? I had not planned to discuss the bias circuits today, but this is how you see feedback circuits everywhere, right? Something the equivalent of a two-stage op-amp. Even in regular biasing circuits, you see this. You will need to know how to do it correctly. Okay. So maybe for a two-stage op-amp, it's okay to have some error in mirroring. Okay, after all, it will change the GM slightly and it may be okay. But there are other circuits where you want accurate current mirroring, and this is how we would do it. Okay. I mean, let's say you are making a DAC in which you need accuracy, and the DAC quiescent output is some particular value. It may be 0.9 volts in a 1.8 volts technology, and you want accurate mirroring, then you will use something of this sort. Okay. And one of the things is this type of thing is being used more and more in bias circuits, because with shrinking geometries, the GDS is reducing. Okay. So maybe in 1 micron technology, we just diode connect it and the accuracy is good enough. Now with 0.18, it's not. Okay. So, and we have designed some circuits in 45 nanometers, and there, if you vary the VDS by 100 millivolts, the current just goes all over the place. The characteristics of the MOSFET, we still draw textbook pictures like this, but in that I think it looks probably something like this. So there again you need accurate mirroring for everything. Is this idea clear? I can use an op-amp around a transistor. Instead of diode connecting it, I use gain. Okay. Still it follows our principle of sensing the current at the drain and feeding back to the gate. Now, I want to keep this this particular node at the right quiescent voltage, so I use a differential pair and feed its output. Now, because I used a differential pair with a high gain and a relatively low frequency output pole, I need to further compensate it. So I can do this. Okay. So let's say I didn't want to bother with compensating this, but I still need this quiescent voltage to be the same as 0.9 volts. But I don't want to go to this two-stage op-amp scenario and compensate it and so on. What can I do? Oh, see, the output voltage is on the lower side, right? It's the NMOS gate voltage, and the input voltage is in the middle. So for the input voltage, it doesn't matter. So if you look at it, with a PMOS input op-amp, the output can swing low but not very high. Okay. Similarly, with an NMOS input op-amp, the input can swing high but not very low. So if your reference transistor is PMOS, you use an NMOS input pair, and if your reference transistor is an NMOS, you use a PMOS input pair. Okay. So let's say I didn't want to do this. This is the picture I have. Okay. In open loop, if I break the loop and examine it, the pole at the output will be of the order of GDS by parasitic capacitance, and here also if I use a differential pair, it will be of that order. Okay. And here also it is GDS by CP. Okay. And the gain of this is of the order of GM by GDS. What is an alternative way of not letting it become unstable? When will a circuit become unstable? When the loop gain is too high and the delay is too much. Okay. Now this is the extra block that I am adding. It has a gain of the order of GM by GDS and pole of the order of GDS by CP if I use this particular circuit. Okay. So can I make something that still has a differential input but has perhaps a lower gain and a higher frequency output pole? Oh, this one. I will connect the other. What will I do? I will do this. Should I do this? What is the gain from, so what will be this voltage then? VGS, and what is the gain between this input and this output? 1. The way it is connected, it is 0. Okay, because whatever it is, however the currents get distributed in these two transistors, the total current through this combined diode connected device is I0. Okay, so this voltage never changes. But you are close to the solution. What you need to do is separate diodes, that's all. Okay. So all I need to do is this. Okay, this is also an amplifier. So where will what will I do? This is the output now. Okay. For this particular op-amp, I will use this circuit. What is the pole? It is GM of this transistor by CL, CP. Okay. And what is the gain? So let me again label it. What is the gain between the differential input and this output? It is GMA by 2 divided by GMD, right? You get half because you're only, the incremental currents will be half of the GM times the differential voltage. Okay. So this is what is most frequently done. You don't want to sit and muck around with compensation of a two-stage op-amp. Okay. Oh yeah, absolutely. Because this circuit now is perfectly symmetric. The suggestion was can I flip these signs and take the output from this side? Then? Oh. Okay, the other one. So I don't diode connect it, but I connect it here, is it? So yeah, now. Yeah, let's see what happens here. So now the suggestion is I will take the output from here and flip the polarity, the input polarity of the op-amp. Will this work? Huh? Yeah, so there are a couple of problems here. What will be the node voltage at this point? In absence of mismatch, it will be equal to the VGS of this, but there will always be mismatch. So this will either go to ground or very high values. So once that happens, you don't have the differential pair operating properly anymore. Okay, so let's say this ends up at a very high value. This MB will go into triode region and probably the current source also. So you will not have enough gain through the differential pair. This voltage will not be defined. So that's why you cannot do that. Okay, so what you do is, pardon? No, but it may not. Total load current may not be constant because if this goes very high, this goes into triode region, this node also goes high and this also goes into triode region. Yeah, but you will always have mismatch, right? So in practice you cannot use this because you just cannot define this node voltage. In practice you will have mismatch between everything and everything else. Okay. So that's why you can't have circuits like this. Okay, operating in open loop, meaning if you operate it in open loop, what will happen is most likely bias point will be where one of these transistors is in triode region because of the mismatch. Okay, so the likelihood of it sitting right in the middle where you want is very, very low. Okay. So what you essentially do is you have to diode connect the other side also. Okay. So this is the circuit we have. Pardon? Okay. I'll have a capacitor here. Okay. So basically I connect 0.9 volts. I mean, which is the input of the buffer? Is it this way? This way or the other way? This way. Okay, so what will be this voltage? So there is no DC negative feedback at all now, right? Where is what causes this voltage to be anything? There is no DC negative feedback setting this particular voltage. Okay. So what will again most likely happen is, this voltage will discharge to 0 because of some parasitic current paths. So this will not be carrying any current, and this voltage will rise up to VDD, sending this particular current source into triode region. Okay. Otherwise, you mean why doesn't it happen if you do the correct thing? No, I didn't get your question. Oh, he said instead of using a differential pair like this, he will make only an AC feedback path around the transistor and make sure that this is biased at 0.9 volts by forcing the drain through a buffer. Okay, but the replica doesn't work without DC negative feedback around here. Okay. So this is also why you need to understand feedback circuits very well, right? So it will come everywhere, even in bias circuits. Of course, we make op-amps with the intention of using it as amplifiers, but you will have it everywhere. I mean, maybe simpler bias circuits. Maybe the speed of this is not so important. I don't think you really go and optimize it for the best unity gain frequency. But at least you should be able to design it stably enough. Okay. So we have two techniques. Let me look at the second one now. So this is diode connected. Right. Now the circuit design is not yet complete. Let me call this IA. Okay. What should be the sizes of MC and MD? Can it be anything? Okay. What is the voltage we want here? 0.9. Okay. So let's say it is operating as desired and it is at 0.9 volts. Okay. So what will be the current here? If it is, because of symmetry, it will be IA divided by 2. Okay. So that causes a particular VGS here. With that VGS, this should be carrying IREF. Okay. Otherwise, you will end up with a systematic offset. Let's say the voltage you need here to have IREF at this point is such that this is not IA by 2, but this is IA by 2 plus delta. Okay. Is this argument clear? No. I need certain VGS at the gate of MREF for it to carry IREF. That is what the feedback op-amp is supplying. Okay. The feedback adjusts this gate voltage so that it is sufficient to carry IREF. Now that voltage must be the output of my auxiliary amplifier. Okay. Now that voltage is also the gate source voltage of MD. Okay. So let's say at that particular voltage, the voltage at which you have IREF flowing here, this current is IA by 2 plus delta. Okay. It's more than IA by 2. So what will happen? So what should happen rather? This will not be at 0.9. Where will it be? Above or below 0.9? Below. This current is more than IA by 2. So this should be above. So this will be at 0.9 volts plus some delta. Okay. So this is again related to the DC gain. We got away by using a low gain DC amplifier, low DC gain amplifier. Our stability concerns went away. It is stable. But it also means that there will be a systematic offset if you don't ensure current densities in this and this to be the same. So this you can do, right? You are designing the current sources yourself. So you can make sure that the quiescent current density here and here are the same. So there is no systematic offset between the quiescent voltage that you get and the quiescent voltage that you want. Okay. Yeah. So if there is mismatch, there is nothing you can do. Okay. Random mismatch, you can't do anything for it beforehand. Okay. So if there is random mismatch between MA and MB, what will happen? So this voltage minus this voltage will be the difference in the threshold voltage of the transistors. Let's say we have only a threshold voltage mismatch, isn't it? Yeah. So if you are using this, this one, right? Okay. Okay, that's fine. Okay. So there are two separate things here. Firstly, the effect of random mismatch. The other is systematic mismatch. Okay. Even if you design this, in absence of mismatch, what is the quiescent voltage of quiescent output voltage of this op-amp, the auxiliary op-amp? It is equal to the VGS at this point, right? So you still make sure that the current density in this and the current density in this are the same. Okay, so that you avoid all systematic mismatch altogether. Now the difference is, let's say you didn't make it to be the same. Let's say you had some difference between the quiescent current density of this and this. What happens is, this particular circuit, the one where you have a high DC gain, will have a high overall DC loop gain. Okay, so the effective systematic offset at the input will be smaller. Okay. So that's the effect of DC gain. Higher DC gain gives you higher precision. So let's say at the particular value of VGS for which you should get IREF, let me call it VGS ref. It's understood that this is not a voltage that's applied. VGS ref is the voltage that needs to be here to get a current IREF here. Okay. At VGS ref, the current here will be some IA by 2 plus delta. Okay. Now in this case what happens? You need to have VGS ref at this value, at this node. Okay. Now but left to itself, in the absence of random mismatch, it will go to this VGS, VGSC. Okay. So what will be the systematic offset referred to this point? This should go to VGS ref, but it has a tendency to go to VGSC. Huh? It is, this voltage has to, the quiescent you can think of as VGSC. Okay. And it needs to have an increment VGS ref minus VGSC. And this extra increment divided by the DC gain. DC gain of this particular stage from this input to this output. That will be the systematic offset here. Okay. So the systematic offset is definitely smaller because of higher DC gain, but it is still there. Now when you are designing the op-amp, you just make sure that quiescent current densities are equal so that you don't have any systematic offset, even if you design something like this. Okay. Unless there is some other strong compelling reason to not do this, you just go ahead and do this. Okay, just like we do for the two-stage op-amp. In the two-stage op-amp, you generally make sure that the quiescent current density here and here are the same. Now, there will be some errors because M4, length of M4 may not be exactly same as length of M11. I already said that you design M11 for minimum length, whereas M1, M2, M3, M4 are designed for some particular DC gain, etc., etc. But still, you try to match it to the extent you can. Now, the second aspect is random offset. So, this, if you have random offset in the op-amp, okay, we can just analyze this at the op-amp level. This is 0.9 volts. And let's say the op-amp is modeled with an input referred offset. Okay. And the input referred offset typically comes because of random offset. Right. Generally you design out the systematic offsets, you get random offset. What's the effect of this? What's the effect of this? So this has to be at 0.9 plus V offset. So you can't do much to the random offset. Now if the random offset is very high, then you will have to design this particular auxiliary op-amp for a smaller random offset. Okay. This is not likely to be an issue for biasing. If you are using this circuit only for biasing this, biasing an op-amp, biasing another simple low precision circuit, it's not an issue. But that can be an issue also sometimes. Okay. So the bottom line is you design your circuits to minimize systematic offsets, but random offsets is something you can't help. That is, at least you certainly don't know the exact value of random offset. The only thing you can do is reduce the sigma of the random offset if that is bothering you. Okay. This is okay? Any questions? Yeah. That's absolutely right. But so in that case, you have to take the hit in systematic offset. Okay. Because maybe getting a high GM out of M11 is more important than trying to match the current densities, right? Now let's say you go to the other extreme, you try to match it and make the length of M11 also 10 microns. And you try to get a large GM from it. It will have an enormous width. Okay. So in that case, your high frequency performance goes for a toss. So you do take some hit in DC performance, DC offset, if you design it to be unequal. But generally, maybe you can take a little bit of a hit in the systematic offset. Okay. The other thing that sort of works in your favor is, let's say again, I will think of it as the quiescent output of this stage. Okay, it has a tendency to go to this value, right, in absence of mismatch. But this in closed loop, the current through M11 is the same as current through M12. So let me call it I11. To carry I11, this has a tendency to go to some value. I mean, this has to go to some value, VGS11. And this is VGS3. So VGS11 is the voltage needed to carry I11 in this. Okay, and VGS3 is the quiescent output stage of the first op-amp. What is the systematic offset? VGS11 minus VGS3 divided by the gain of the input differential pair. Okay. So it is GM1 by GDS1 plus GDS3. Now in the particular case that you mentioned, you have made the length of this 10 microns or something very large. Now that whole point of doing that, I assume, was to get the GDS values down. Okay. So, I mean, to get a large DC gain from the first stage, right? Yeah, perhaps also. Yeah. It increases the DC gain. So it does get divided by the DC gain. Okay. So it may not be such a severe effect. There will be certainly some effect, but maybe not such a bad effect. Okay. So the systematic offset reduces if you have a large gain in the first stage. Let's say you use a cascoded first stage, a telescopic cascode. Then even if this voltage moves by about 50 millivolts, it's not a big deal, right? It will just add to a very small value of systematic offset.
So my argument was that instead of using a simple stage, we use a cascoded telescopic one. We anyway don't need any swing at the output. So
why?
Like, we don't need a large swing at the output in first stage.
Why not? That depends only on the second stage gain, right? Yeah.
So if we do this, then we would have to care about a lot of systematic offset that will come and all.
Yeah, that's true. So you can try and design that. The only thing is you can design a telescopic cascode for the first stage. That's what you're saying, right? Yeah, that's correct.
So that is actually with respect to whatever is given in problem 4 of this.
Yeah.
So there I have to make, if I keep a minimum length, my offset, systematic offset was value somewhere around 1.5 or 2 million.
Okay.
Very simple.
Yeah.
So in the telescopic,
See, again, your choice between telescopic and simple differential pair may not be governed by systematic offset. Okay. When you use a telescopic cascode, you do get additional parasitic poles, etc., and you have to design all those additional bias sources and so on. So it may not be always something that you want to do. Okay. You certainly can do it. Yeah. You can use a telescopic cascode. Okay. So we are past the hour. Do you guys have like 10 minutes now? Or you have a class now? Actually I had wanted to discuss the slew rate of this, but I think we are out of time. Maybe we can discuss it very quickly and then leave. What is the slew rate of this amplifier? What limits the slew rate? Current through M12? Okay, let's, because we are out of time, we will work it out quickly. Let's say that, first of all, let's neglect RL. Okay, generally it's only capacitive stuff that matters for slew rate. So let's neglect RL completely. And let's say the output is ramping up at a certain rate. We'll work backwards from there. We'll assume that the output is ramping up at a certain rate and see whether it's possible or not. Okay. The output is ramping up at the slew rate, at slew rate plus. Okay. So what will be the current flowing here? What is the current? It's a ramp. It's a linear ramp. Slew rate times CL. That's all. Okay. If the voltage across the capacitor is changing at a certain rate, the current through that is the rate of change times the capacitance value. So this current is CL times SR plus. Okay. What will be the current through CC? Let's again neglect RC. Okay, it's not going to have much effect. What will be the voltage at this point? What will be the voltage swing? Current through CC will be? Why? The output is ramping up at a certain slew rate. What is the current through this? So, what will be the voltage swing at the input of M11, at the gate of M11? It's the output voltage divided by the gain of the second stage. Okay, roughly speaking. And let's assume that the second stage also has a large enough gain, let's say 10 or something. So, this is almost constant. Okay, this is a relatively crude approximation but works. So, what's the current here? Same. Okay. Okay. What is the current through this? It's a bias current, right? It's just I12. Let me call it, or I1. I think I used to call it I1. Let me call it I1. And what is the current through this? So it's just Kirchhoff's law, IL plus I1 plus all of these things. Okay. So what limits the slew rate here? Swing of the first stage output, that's it. So first, that is true. That is, you have to have, the current here is I1 plus this plus this. That much current must be supplied from M11. For that to happen, the input, I said it's almost constant, but it has to go low enough. Okay. But let's say the swing at the output of the first stage is low. It is not a big concern. What is the limitation here? Where is this current coming from? The current through CC? Huh? Yeah. No, it is coming from this side. It has to go here, right? So it has to come from the first stage. What's the maximum current that can be delivered from the first stage? I0. Okay. So the maximum current available for discharging this capacitor, neglecting every parasitic here, is I0. So the limitation for SR plus is, okay, that's all. Is it okay? So we have assumed several things, that this voltage is almost constant, the gate capacitance and other parasitics are negligible. So all of the first stage current is going into the compensation capacitor. Okay, in that case, that's the only thing that limits the rising slew rate. What about the falling slew rate? So the output is ramping down. Output is ramping down at SR minus. So how will the currents look like? Which way will the current flow in CL? Flows into the op-amp, and the value is again SR minus times CL. What is the current through CC? Again, we make the same assumptions as before. So what's the current through CC? SR minus times CC. Okay, because this node is changing, this node is not changing all that much. That's the assumption. Okay. Of course, it will have to change, but we just assume that it is not significant. So what's the limitation now? So there are two limitations. First of all, this SR minus times CC again has to come from the first stage. The maximum value of current equals I0. So, and what about this other condition here? This is a fixed current, right? Unlike M11's current was changing in response to the gate source voltage. And the gate source voltage responds to the input. Okay. You can pump more current through this, but the amount of current that can be drawn out is, the maximum is I1. Okay. The best case is when M11 is completely cut off. Right? When M11 is cut off, a total current of I1 can flow through CL and CC. Is this okay? So this again, like we have already seen this several times, the second stage current has to be more than the first stage current, right? Just from these two equations. So evaluate these two limits and then see which is the lower one, that will be the slew rate. So obviously you don't want one of them to limit it. Okay. You don't want to use a small current in the output stage and limit the slew rate. Right. So you have to use currents in proportional to CC and CL. In proportion to CC and CL. If you don't want one of the stages to limit the slew rate. Rather, if you don't want the output stage to limit the slew rate. Okay. So on one side it is limited only by the input stage. On the other side it's limited both by input and output. Because the current that can be sourced out can increase a lot in response to the gate voltage here. Whereas the current that can be sourced in cannot be increased because it's a fixed current source. Okay. So that's all I wanted to discuss. That should enable you to design the two-stage op-amp.